is Delaney.
This is our video lab report for Lab 7, the Michelson Interferometer for OPTI 380A.
And this is our video for the Wednesday lab section under Lam Nguyen.
Part A. In this part, we found the calibration factor, which relates the reading on the micrometer to the distance moved by the mirror in the Michelson Interferometer. This was accomplished by shining a helium neon laser of wavelength 632 nanometers through the interferometer. We aligned it by first shining the beam into the input of the beam splitter and then adjusting the mirrors so the reflected beam overlapped itself in the image plane and the reverse reflection passed back into the barrel of the laser. Once this was aligned, we placed a lens in front of the laser to view the fringes of equal inclination on the viewing card. The micrometer reading was recorded, then very carefully adjusted to collapse exactly 100 fringes. The new position was recorded, and we found the calibration factor using the equation on screen. By dividing a difference in micrometer readings by the calibration factor, we get the distance moved by the virtual image. The 1/2 factor in the equation accounts for the doubling of distance traveled caused by the mirror. The equation for the calibration factor is derived from the first equation on screen, which relates the movement of the mirror to the fringe order.
Now that we have our calibration factor, we continue into part B where we measure the wavelength of various sources. We start with a laser diode, replacing the Heaney laser in the setup, still viewing the output on the card. We recorded the first micrometer position, then carefully collapsed 50 fringes and recorded the new position. Then we divided our difference in micrometer position by our calibration factor to get our difference in source position. This delta D was then divided by delta M to get the wavelength of the source. This was repeated for the sodium lamp and a coherent mercury source. These, however, were not collimated sources, so instead of viewing the interference pattern on a card, we placed a phone at the output of the interferometer to get a clear view of the pattern. We found wavelengths of 669 nanometers for the laser diode, 520 nanometers for the mercury lamp, and 595 nanometers for the sodium lamp. These are very good values given the difficulty of accurately counting the fringes. Here you can see an image of our interferometer when illuminated by the sodium lamp, and the fringes of equal inclination coming from that source.
Finally, in Part C, we found the wavelength separation of the sodium doublet. The basic theory behind finding this is that when two very close wavelengths overlap, they will interfere with each other and have a main carrier wave at the average of their wavelengths and a much slower beat wavelength where they will alternate between constructively and destructively interfering. To find the wavelength difference, we measured the position of 3 nulls, or where there was the maximum destructive interference, where the pattern appeared weakest. The average difference in position between the nulls was taken as delta D. Then using the equation on screen, we calculated the difference in lambda as 0.65 nanometers. This is a very good result compared to the expected value of 0.6 nanometers.